This is Lab 5. Here's a table of contents for what will be discussed in the lab. We'll have an introduction, then our physics principles used, look at our experimental procedures and its results, and then we'll view the simulation in GlowScript, interpret these results, go to the what-if scenario, and end with the conclusion, including potential sources of error. So for introduction, the purpose of this lab is to observe a bar magnet as it is dropped through a solenoid and to see how the force from the magnetic field affects this motion. The goal was to find the magnet that takes the longest time to travel through the solenoid and calculate the force created by the magnetic field, and then write a code in GlowScript to simulate the motion and return a model with the time that the magnet would take to drop through. And then a brief look into the result. The bar magnet fell slower through the solenoid than it normally would fall when dropped. The physics principles used, we have the equations for the magnetic fields and then the magnetic flux equation, and then we also used the EMF calculated from the magnetic flux to find the current in an induced loop, just doing EMF divided by R. And then we also utilize the force of the magnet on the loop, and we see that the force back on the magnet is equal and opposite because of Newton's third law, and then the net force is the force on the loop minus the force of gravity. The procedures for the experiment was first to find the north side of the bar magnet, and then with my smartphone camera record a video of the bar magnet dropping through a tube of aluminum foil. We then had to measure the length and thickness of the aluminum foil roll, and then to use those calculations to measure the total time taken for the magnet to drop through, and then measure this time, and then also measure the time for the magnet to drop naturally. And as a result, the bar magnet took longer to reach the ground when it dropped through the solenoid. So here are the specific results. The aluminum foil roll, the thickness was 0.8, its radius was 4.1, and the length was 45.5 centimeters. And the bar magnet, from the previous experiment, we already saw that mu was 3.55 and m, the mass, was 0.023 kilograms. And after 5 trials of dropping the magnet through the foil, just calculating the time on my phone, the average time was 2.54 seconds. And then without the foil, if it were dropped normally, this could be used with the kinematic equation, which was calculated t to be 0.305 seconds. And as we see, 2.54 is much greater than 0.305 seconds. Moving into the GlowScript code for the simulation here. Over here, we see aspects of the aluminum foil and the magnetic field and flux equations utilized. And then we also see, we track the location of the magnet with this here. And then we also calculate the force of the magnetic field. And then we return the time for the magnet to travel through the entire loop. And then the results from GlowScript. The code modeled the magnet falling through the continuous rings, and then the magnetic field flux and current induced in the loops was calculated. These values were used to calculate the total time it takes for the magnet to drop through. And the model predicted the time was 3.217 seconds, and as we said it before, our time was 2.54 seconds. And here we see this was before the magnet is dropped, and then this is when it is all the way at the bottom, and then we see the velocity versus time graph here. So these results, we know that red, it was counterclockwise, and blue is clockwise, just the way the magnet rotates in order to slow down in the tube. And then the magnet would still slow down, but the currents would flow in opposite direction if we flip the magnet around. And then the model calculated time to be less, as we said in the previous slide. And the shape of the graph suggests that the magnet experiences force while inside the tube, and this force goes away as it exits the tube below. Our what-if scenario. What if the resistivity of the conductor were reduced as close to possible to zero? The braking force experienced would increase until it equals the force of gravity, and the magnet would never exit the tube in this situation. Similarly, if holes or slots were cut into the tube, the current through the rings would be interrupted, and the force on the magnet would be reduced. And then our conclusion, as we said before, a magnet takes longer time to fall through a solenoid, experiencing magnetic force as opposed to just falling to the ground normally. And the main error in the experiment was the error calculating time for the magnet exiting the tube. It had to be very precise to get the most accurate data. And it was difficult to get the timing perfect when the magnet came out of the aluminum foil, which caused the most error in our data in the experiment. Thank you.